Okay,
Here we are.
we are live.
Yeah.
Okay, let's start. Okay, welcome everybody to this new Ticino Softwarecraft meetup. This evening we'll have a lot of fun with Francesco Gualazzi, and we'll have a lot of fun with the nerdy stuff that we like a lot. Just a few words before starting. These are the bad faces behind the Ticino Softwarecraft community. Why Ticino? Because, well, this community originally was founded in Ticino because the founders, the people you can see in the slide, work together in the same company, and then later on we changed company, and during COVID time we moved from physical meetup to online meetup. Honestly, this slide is here just because Giovanni Panice wants to have here, and probably is the only software developer that is believing in agile again in these days. And we started with these values that are the software craftsmanship manifesto values. And we follow these values to also as a guide to organize our meetup and the people that we have in our meetup. Let's go ahead. Here you can find us in several social channels. LinkedIn, DevTO, YouTube, and so on. So if you want to reach us, if you want to participate, having or organizing a meetup or stuff like this, you can contact us on our social channel. So move ahead, let's go, and we can start with Francesco Gualazzi, that this evening will present us Zig.
Hi there, good evening everybody, good afternoon, good morning, wherever you are. So happy to be here, and thanks for the introduction, Marco and Giovanni. Thanks for all the folks that invited me to do this talk. I'm very grateful because Zig is, the earliest of my passions. I've been using it for 18 months, bit more than that now. And I started, trying to spread the word about it because it seems that it's a little bit underrated, in my opinion, for what it offers. I hope that there is a lot of you that has never read or written any Zig code watching this talk. If that's the case, my goal is that I inspire you with enough curiosity so that you during the talk or after the talk, you go and install the binary in your computer and you start tinkering with it and, play with it and have fun just like I did. You can find all the slides and the code that I'm going to present during the talk in this URL. If you have a smartphone, you can scan the QR code and it will bring you to the GitHub repository. What we're going to do today, I'm going to present the language and the tooling around it. We're going to look at some code, so actually see some Zig in action and how it delivers some of the values that it sponsors. And finally, I want to explain why I think Zig is really relevant today, and it will become much more relevant in the upcoming years, in my opinion. And finally, we are going to have some Q&A just to understand what are your thoughts about it, what you didn't understand about the talk, and what you want to discuss. Everything can be shoot at me. I hope I can reply with meaningful content. You can hear my dog in the background? Maybe not. Okay. So what is Zig? I took from the website, the official website, zigland.org, The slogan and the motto, the presentation that the Zig has, Zig is a general purpose programming language and toolchain for maintaining robust, optimal, and reusable software. You can see that I highlighted the most prominent concepts of this phrase. So general purpose, it means that it is targeting all the platforms from embedded to desktop to WebAssembly. You can use it for everything. You're not limited to certain use cases. Robust, optimal, and reusable software. This is the core philosophy of Zig. Once we build a piece of software that solves a problem, what we want to do is make it efficient, make it performant, and make it solving the problem in a way that is done. We have to cover all the edge cases, all the possible edge cases, and we want to make that compiled as a library so that anyone else can build on top of it on the software that we wrote and solve a problem specifically just by importing some code. What is not highlighted in the text, which is also what is very important about the Zig philosophy, is the word maintaining. This phrase, this sentence could have been spelled like Zig is a general purpose programming language and toolchain for developing robust, optimal, and reusable software, but instead maintaining was chosen because one of the key ideas of Zig is that software should be maintained, software should be incremented and improved over time. So if something is already solved, maybe in another language that speaks the C ABI, maybe it's written in C or C++, there's no need to reinvent the wheel. So what we have to do actually is maintain that project, understand if it needs to be fixed or brought to a new version or have some extensions applied or improved, and then reuse what's already solved for our purpose. In fact, if you go into the ziglang.org website, you will also find the motto that is maintain it with Zig. That is to say, because how Zig works, if you have a C project, a code base that is delivering some functionalities in C or in C++, you can extend it with Zig. You can build it with Zig because Zig compiles C code and C++ code, and you can merge C and C++ code with Zig code, so extend functionalities. And we are going to see that also later. ZigZen is the functionality of the binary that displays this philosophy. If you, like me, install a binary for the first time, I always do Zig. I fetch a binary and then run the ---- help. So when I did that, I was curious about this last option, and I ran it, and that's what it does. So we can see this is summarizing the philosophy of Zig points. So I always do that. I fetch a binary and then I run it with help. And I was so curious to say, what is this Zig doing? And all of these points, really, they are all very important. They all resonate with me a lot, especially edge case matter, the second one. Compile errors are better than runtime crashes. So if we can shift left problems that we can detect in the compilation phase, and the compilation speed is reasonably fast, and we can iterate much faster and avoid certain bugs to arrive in production, even before the CI pipeline runs. Focus on code rather than style. The idea here is that we want to debug what the software does, not how the language works. So the language should be simple to read, should not have hidden control flow, should be expressive about the intent, and should exactly communicate what's going to happen at the machine level when it's going to execute. And finally, the last two, these are my two favorite. Memory is a resource. Zig does not have garbage collection. You have to do manual memory management, just like in C or C++, most of the times. So what you're faced with when working with Zig is managing the memory yourself using an allocator freeing the memory when it's not needed anymore. And there's a lot of tooling around this concept that is improving the experience that you would have with C. And there's a lot of also of possibilities that you can achieve thanks to this philosophy, thanks to this tooling, because when memory is a resource and there is no memory, you can handle an error if an allocation failed. And this is tremendously important to, manage edge cases. And the last one is my favorite. Together we serve the users. All we do every day, when we write software, we don't write software just for the sake of it. We need to write software because it must be used. It must be run by someone, either a machine or a human. And the user of that software is what really matters. We don't have to focus on anything else than solving a problem for our users and solving it in the most optimal way going forward. So with that, all of this philosophy, how does it translate into the practical implementation that we see in the Zig? A bit of history first. Zig was announced publicly in February 2016. Andrew Kelly, the creator of the language, was working on a personal project, a digital audio workstation software. He was trying to develop this program by himself. And most of the libraries that are related with managing device access or sound management, they are written in C, of course. But he was very frustrated with the ecosystem around these C libraries because the build system was messed up. You have to use different tools, auto tools, configure, make, CMake, whatever. And so he came up with this idea and say, why I don't develop my own language where I can actually remove the bad parts from C and the build system and actually reuse this software that is already working fine, but build it in a simpler way and consume it in a simpler way. So he started working on Zig. And for the first 4 years, it was just like a pet project, and he was trying to gather sponsorship from GitHub. In the 4th to 5th years, it gained a lot of traction because he was presenting it here and there into conferences. And the people really liked the concept that we can have a better C, we can have simple software that delivers good performance and makes and let the users make, the developers make a good decision about how to roll out certain features. So after the 5th years, he founded the Zig Software Foundation, which is a real non-profit. So just like the Wikimedia Foundation, it's a company, it's an organization with a board, and it's a company that must reinvest every money that it gets, every profit that it has, into improvement of the Zig language and the Zig ecosystem. So it's not an evil corporation that wants to grow at the expenses of users. What it has to do by its statement, it is improving and paying the developers and improving the contributions to the language and making it resilient and robust for future iterations. I should mention Zig is not 1.0 yet. The current stable version is 0.13. There is a 0.14 going out in a couple of weeks. I think the deadline should be March 3rd, so probably next week, but I don't know yet if it's been postponed. So expect a 0.14 stable version to be released soon. And also expect breaking changes between these minor releases because it's not stable. The tool chain that you get with the Zig binary, when you go to Zig or ziglang.org/download, you fetch a binary for your platform, OS and architecture. And what you get in the binary is already, everything is self-contained in there. You can have a compiler for the Zig files. You have a testing framework within the standard library that is also compiled with the code. You have cross compilation natively from one machine into myriads of targets, from RISC-V to PowerPC to ARM64, whatever. And right now, this cross compilation is based on LLVM and Clang. But there is in 0.14 an experimental backend compiler, or compiler backend, well, an experimental backend for the compiler that only do not use LLVM at all. So it only uses custom handmade machine code generation, starting from the LLVM bitcode. Now, the good thing of this binary that you get from the website is that you can start immediately to integrate and to build existing C code bases with this binary, because it also embeds a part of Clang, and it also embeds WebAssembly compiler. So you are going to have immediately, with just one binary, immense possibilities for building and compiling software. The binary also comes with a dependency manager, just like npm for Node.js, but npm is a separate binary. So you do zig fetch, and you share it with the GitHub URL with an archive or a tarball, and you will have a build.zig.zone, which is a Zig object notation, so basically a Zig file that describes your dependencies and that is integrated in the build system. And last but not least, the community is really amazing. So there is a Discord server with, it's a pretty big Discord where there's a lot of people always online, and you can get answers. There are a lot of help entries, and there are discussions about how to improve and problems that someone faces. I really recommend you to join the Discord if you want to start working with Zig. Software You Can Love is a conference that should have been done annually, but I'm not sure this year will be done. And it's a conference that is mostly dedicated on Zig. Last year we had one in Milan, and the year before it was in Vancouver, if I'm not mistaken. And it's really a place where all the people adopting Zig in the world gather and stay together for a couple of days, maybe 3 days, to share ideas and discuss about future improvements and also work on projects. So it's very fun. I hope we can have a new session like that earlier or sooner. And Zig Showtime, finally, I leave it here, is so the link is zig.show, is a live stream where Loris Crow, the vice president of community, will present several topics, starting from game development with compilers. It's very interesting show to watch.
Yeah, yesterday I saw a live showtime by Christoph. Yes, about a graphical library. Very interesting, really.
DVUI, right? Yes.
Yeah.
Yeah, nice one. So how does Zig delivers on all of these features and all of this philosophy that I showed earlier? I cannot present the entirety of the language. I will bring 3 items that, in my opinion, are what really make Zig stand out from other languages that I've been using so far. And the first is the syntax. I have 2 slides here for the syntax. Again, I'm not going to cover the entirety of the keywords that are available in the language, but I want to highlight some points that I found really pleasant to work with, and then some of them I really missed in other languages that I've worked extensively in the past 12 years. For example, comments. There are 3 types of comments, and you can have package comments, API, public API documentation comments, and source code only documentation. So only comments that are only visible in the source code. This means that you can keep your documentation in the code, and you can generate documentation that generates HTML files from the code itself. Actually, if you write a test that is named exactly like the object that you are testing, that's also going to end up in the website generated as a test that validates the API. The expression of mutability is very evident. So you have these 2 keywords, const or var. Any variable is either a const or a var. So you can have const pointers, you can have const variables, const references. If it's a var instead, it's mutable, and it's it's very easy to see what has to be changed, what can be changed, or what doesn't have to be changed. You have enumerators and algebraic data types, which are referred as tagged unions, which I guess comes from C. So the classic union, where you have a list of types that can fulfill the union, and only one is active at any moment. You have the enum, which is a set of values that you want to assign, so a set of descriptions. In reality, these are integers, so it's like a list or set of entries that you want to define. Then you have a union enum, which is the tagged union. So here you can characterize the type of the union with an enumerator. And these are very helpful, and you can do a lot of things with them, because both enum and union enum, they can have methods, and this is very helpful when you want to build data structures. The optionals, it's something that I've been missing in Go for ages. I don't know why we have this syntax in Go that if you want to create an optional, you have to pass a pointer to that, and if it's a nil pointer, then a modern language must have optionals. And in Zig, it's very simple. When you declare a type, if you prepend the question mark to it, that type is optional. So that thing can be null or not. In fact, optional to pointer t can be null, but pointer t can never be null. So you cannot assign or deassign a pointer in Zig. That's one of the fixing one of the biggest mistakes that are available in C and produce undefined behavior, but are available also in other higher level languages. So it's almost impossible to produce a pointer reference in Zig. Or else is used to assign a default value to an optional that is null in any given moment. The syntax to unwrap the optional and to work with the value that it contains or no is using the if and then putting the optional into into parentheses, and then capturing the value of the optional into the pipes, and then you can consume it into curly brackets. Or if it's null, you can put an else and do in the null case. Defer and defer, these are two keywords that allow postponing the execution of any piece of any block of code that is appended to them. These are different because defer will always execute at the end of the block that is declared in, and a block is anything that is between curly brackets. So RDefer will execute at the end of the block unconditionally. It will always execute. And RDefer instead, it will run only if the end of the block returned or exited with an error. So if in that block an error is raised or bubbled up, RDefer will be put to execute just before the end of the block. In fact, this ties into the error handling, which in Zig is done very similar to what is done in Rust. So it's using a result or a result type, which means that it's a union between either a list of possible errors or a concrete type T that we return to the user. In fact, you can declare any fallible or any function that can fail. You can give it a return type of any error, !T, which means that the function can return any sort of errors, or a type T. You can also remove the any error and let the compiler infer the set of errors that are going to be returned by the function. And this, by all means, equals to declaring that you are returning a union, so either an enum of errors or T. To handle errors in the code, there is either try, which bubbles up the error if it's presented or returned by the function, or assign the concrete type to the value that is on its left. Catch is used to intercept the error and execute behavior. So instead of bubbling up, the error is returned to the local function, and you can act upon it. For example, executing other code or logging, whatever you want. a similar syntax to catch is using if function call and then capturing the value, the concrete type t in the value, else capturing the error. So this is very useful if you want to handle in the same function both cases and you don't want to bubble up the error to the caller. Now I'm explaining all of this and then we're going to see the code. The syntax continued. This is a part that is a bit more convoluted, but I hope that I can show better in the code. Unreachable is a keyword that is basically telling the compiler that we don't expect that branch to be reached. And in fact, unreachable is if unreachable is reached in any runtime execution, it will bring into a panic in debug mode or will be undefined behavior in other release modes. And this is because the compiler, when you use unreachable, performs optimizations to effectively discard the branches that are marked with unreachable. It is helpful for iterating, and it is sometimes needed for example, discarding errors in a defer. But I just want to mention because it's also in the code and it's also decent part of Zig code that you see around. No return is one of my favorites. Basically, no return is actually a type and it's a set of type of all the execution blocks that do not return. So if you have a break or if you have a return, obviously that's the opposite type of no return. And when you declare a function with no return, the compiler is able to understand if the function will ever return. And if the function would ever return, you would get a compile error. So this is very helpful for embedded systems, where you want to basically run a main thread, a main loop for the entirety of the duration until there is power to it. And I just wanted to mention here because I found that a language that exposes already this concept is already, let's say, giving us instruments to work with that are not even thought of in other languages. Thread local is a concurrency helper, if you want. When you declare a variable as thread local in a global scope, you can pass that same variable or a reference to it to multiple threads, but every thread will get their own copy of the variable. So they're not going to be able to interfere with one each other. They're going to mutate also or read their own copy of the variable. So that's very helpful if you have, for example, a fan-out pattern where the same value needs to be passed to many threads, but you don't want the value to be mutated. This built-in is for you. This keyword is for you. The arbitrary with integers I also find amazing. You can declare any size, any width integer from U0 to U65,553, which means that you can have arbitrary integers and you can stack them into structs to perform better alignment. This is crazy, and we will see that in action later. This is tied with packed struct. When you declare a struct, which is like a type or a structure, if you prepend it with packed, it means that the compiler will preserve the field order in the memory. So whatever you declare as a packed struct, you are guaranteed to have the same structure in the memory that is allocated for that struct and is populated for that struct. So together with arbitrary with integers, this allows, for example, to perform optimizations to keep an entire struct into, 4 bytes, but using, 3 integers. And that's very powerful. And finally, the link here to built-in functions. These are all functions that are available in the runtime with @.
Francesco, one moment. We have a question about unreachable. So, some minutes ago, but I don't want to stop you. So, Angelo said, this can never happen about unreachable. I didn't get so much what Angelo wants to say, but I think that maybe...
So unreachable. So let's clarify unreachable. Unreachable is a keyword that lets you define a piece of code that should not be reached. So when you mark that a function would return an error, if you say function call catch unreachable, it means that you don't expect that error to fail ever. Because if it's returning an error and you catch an error and that catch is unreachable, then you are telling the compiler this should not happen. That's why it goes into a panic and prints a stack trace in debug mode. So telling the source code, telling the compiler that thing is unreachable is, let's say, a shortcut to avoid to enter problematic paths. The problem is, you shouldn't abuse it, because when you actually enter that path and you are not in a debug mode, which is what you usually put in production, that's not going to do anything, basically. So it's a bit problematic. Let's say it's good if you prototype, as I was saying, but often it's better to then replace the unreachables with actual logic to handle what could be wrong.
Anyways, so Angelo said that he was joking about, I think, the token unreachable, because about never happen unreachable. So this was it was joking, Angelo. So, but in any case, it's good to rephrase the meaning of unreachable. So, okay.
Yeah, I just want to show here a random tweet of mine when I discovered that, I mentioned the return here, and I discovered that you can write $no return as a return type of a function, which means that the compiler can detect when the function exits, if it exits, and if it exits with an error. So it basically analyzes all the possible branches that the function would go into. And if it detects that any branch is not exiting with an error, you get a compile error. So I had to use this one actually in a BPF helper that I was writing in Zig, because Zig compiles to BPF as well. And I just tried it out and I say, wait, but no return? I need no return, but I also need to return an error. Let me try to put a question mark and see if it compiles. And wow, it worked. So, and actually I went ahead and tested, I was putting a return in the middle of the code, and the compiler will say, you are returning here, but this function is marked as no return and an error. So either you return an error or you don't return. That was amazing. This was a revelation for me, and I hope you get a same feeling when you are starting to use Zig. What is this? Yeah, so let's go actually and see a bit of code. No, I said in this at the start, there's this QR code and the repository is there. I prepared two files. One is this one that I'm showing, just to display a bit what you can get with Zig. And for example, let's start from here. Documentation, as I mentioned, this is package documentation. It would be rendered in the main website page. Then you have this one that is only visible in the source code. It's not going to be rendered, just like this one. And then finally, this 3/comment, this will actually be part of the API documentation. So you will see it in the website. As you can see, I like displaying code with tests. And writing a test in Zig is super simple. You just enter a test declaring the test keyword. So everything that is marked as test can be run as a test using Zig test, or passing custom build commands. Like in this case, I have Zig build test, which is a command that I added to the build system, because the build is completely programmable in Zig. I will get to that later. So, but let's go a bit in the code. This test shows how the expression of mutability works. Here, I'm declaring a constant variable a, and I'm saying that it's going to be of type signed integer 32. And then I assign to this constant variable the value 42. Then I also declare another constant variable. This is called b. I don't specify the type. And this is a reference to a, so it's a pointer to a. And then I have a third variable, which is called c. And this one is also a reference to a. But this one is mutable, okay? So I have the debug print here where I'm using one of the built-in functions. This is considered metaprogramming built-in because it's fetching the type of the variable itself. And then I'm passing the type here. So here in the print, you see you get the curly brackets and it will infer it for you. So now my question is to the audience, is this assignment possible? Is this going to work? What's going to happen if I run this test? Well, it's as easy as that. We can try run it in two ways. Actually, let me show you the first way first. So if you have any zig file with some tests and it doesn't import other zig files, you can run it like this. So this one is going to run the whole file. I can also add a parameter test filter. And
so if someone from the audience wants to reply, we give them 1 minute. In the meantime, I have a question. So B and C, you didn't write the type. I suppose that is able to infer that is a pointer, no?
Absolutely, yeah. But well, okay. It would also infer if I would do something like this. So this or this. I mean, this also works. Well, of course, I have to say this thing. If I try to compile this test and run it, now it will fail because F and D are unused, so they're not read, if I'm not mistaken. But yeah, so the type inferral is a common thing in Zig. You only need to specify the type when you know there is a doubt about the type coercion. So, for example, if I do this, obviously I can write this, but it would be either F32 or F64. By default, if I'm not mistaken, is F44. But if I want an F32, I have to specify, no? So
okay. In the meantime, Angelo said that well, it should not work if const means what we think, because Angelo thinks that is not Java and an hash map is immutable for
well, actually, let's run the test, and you can see there is already speaking. Now, what is interesting here is that this is not a runtime error. This is a compilation error, right? So the test is first compiled, and then it is run. Okay, and this is a compilation error saying that you cannot do that, right? So, well, let's just comment it. And is this going to work? Because also B is const. So I'm trying to assign C to B in this case, but is it going to work?
Okay.
What do you think? Is it going to work or no? What? Oh, sorry, I messed up. Is it going to work? Oh my goodness, why? Okay. No, it's not going to work as well because it's constant, right? So this is a constant pointer. And it means that I cannot reassign anything to it, but I can, in theory, reassign to the content of the pointer if it's not const, right? So with this syntax here, I'm accessing the content of the pointer using the reference, and I'm trying to set it to 73. Now you can see C is a mutable variable, okay? But it points to A, which is constant value, right? So this will also not work, right? Because, cannot assign to constant because C is pointing to a constant, right? And we cannot assign to that, okay? Finally, I have C equal to undefined, which is a shortcut basically to not deassigned, because it's not actually removing the memory, but is mutating the variable, setting like a memory, a bit pattern that is recognized by the compiler. So the memory is not cleared for C, but we can actually reassign C and treat it as not valid anymore. So will this work? Yeah, it will work because C is declared as a var. So you can mutate. In this case, I'm mutating just by setting it to this undefined fixed pattern. And yeah, you can see the print line has given us the values. So the pointer is 932, and the value for the variable A.
So in the meantime, we have a question. So
I have just one question. When you when you type the test, basically the file is compiled and executed.
Not the file, the test. It's scoped in the test.
Okay. So just the test is compiled?
Well, yes, because I'm using test filter. So const is the name, is inside this test name. This test is named const and var. If I add this test filter const, only the tests that contains this pattern will be compiled and executed.
For example, if we have a module and we test this module, the compilation is just related the module I'm testing.
Yes.
I don't know, a class or something like this.
Yeah.
And all the other code base is not compiled in this case.
It's compiling the module that you're testing and its dependencies.
Okay.
Yeah.
I got you.
Yeah, that's very powerful indeed. This is a very cool feature because, again, if you think about it, there's no need to compile everything else when you are just working on something, and that's very powerful. In fact, working with directory structures and the modules in Zig is very powerful. Well, let's try to run the entire thing, right? So if I remove the test filter, it's actually going to run the entire file. There's a second bug here, which I'm going to speak about earlier, but let's see. Well, actually, no, let's see it in the code first. So we said before, enum is a list, a set of descriptions for possible values that we want to use. And in this case, I have defined an enum with 4 possible entries, right? So the pet is a dog, a cat, a parrot, or a lizard. And then I defined a method. So this is by all means a method that is consuming the same pet type and is defining how each pet makes a sound, right? So each pet makes a sound that is a string. So in Zig, there is not a string abstraction. There is just array of U8s. Well, also the standard library also has UTF-8 support, but most of the times when you want to work with strings, you just declare them as a slice of fixed bytes, right? And we have a switch that is switching on the type of the enum. And what do you notice here? Do you notice something weird? There is probably something that is not making the compiler super happy because there is a difference here, right? So actually, let me write this one like this. So if I try to run this specific test about the enums, which you see it's down here, I'm just declaring a dog and declaring a parrot, and then trying to play the sound of each animal. If I try to run the test and like this, yeah, I got also a compile error because the switch needs to handle all possible cases, and in this case we only have defined 4 entries, but we only are handling 3. So how do we fix it? Either we use else like this, or we actually handle the full spectrum of all the possible types. So I'm gonna say that we also need a lizard, and this is going to do his like this, right? So when I go back and now I try to re-execute it, this time it compiles and it just runs fine. Brief look at the union. The union, it's possibilities. Let's say you can have you can have a single container for multiple types. In this case, an animal is either a domestic animal, so it's of type enumerator pet, or it's a wild animal that lives in the forest. So in this case, it's just a regular string that you can set whatever you want. And the union enum here, so a tagged union, is in where I define a union. So again, type that can be characterized with multiple entries, but the entries are also the list that we want to describe with the enumerator. So the union here is associating a type to any of the entries of an enumerator. And this is very powerful because when you are creating data structures that can be interchangeable, or even, this can help you achieve some polymorphism, because again, here I could have a method, and in the method I could define behavior that is specialized for every of the types that are assigned to each of the enum entries. Yeah, that is enums, and we covered that. Oh, I want to reinforce the errors that we have seen here. These are compile errors. Okay, so the test has not even yet run. The compilation phase is the most valuable asset that we have to detect errors, and Zig really makes this first-class concept of the entire language. So let's go for the optionals. As mentioned, an optional type is marked with a question mark, so it can either be a concrete type value or null. Here I show how it is unwrapped. So when I try to unwrap A, I get 42 in value. And in fact, I'm expecting this to write A is 42. But if I set A to null, this is going to print A is null. So this branch is never reached. I show the debug entry for printf. You can use question mark, and it's going to infer the type for you. And finally, you can use or else to define a default value for an optional that is either null. So basically, this is how you declare an assertion from the standard library testing framework. You see, I have a try because this expect equal can return an error. So if this return an error, I want the error to bubble up in the test and be marked as a problem, so as an error in the test framework. Standard testing is the namespace where all the testing framework lives. And let's just try to run this test. We expect it to pass because, A is 42 and B is null. Okay. And working with optional is really interesting in Zig, especially because, pointers cannot be null, but sometimes you want to define a field of a struct that can be there or no, and must be also referencing another type. So in that case, you absolutely want to use the optional pointer. Defer and defer, it's very important to note that the block definition here between curly brackets is what limits the execution scope of defer, what restricts the defer execution scope. So what do you expect here? I declare a variable to 1, then I defer its increment inside this block, and then we print it. So what do you think is going to be printed here in A? Remember that defer will execute unconditionally at the end of each block. So it was 1 before, then inside this block, it's mutated here with the defer, adding 1. So here is obviously going to be 2. And then I declare another defer keyword in the scope of the test, right? So the block surrounding this defer is the test block. And then this means that when I try to execute this assertion, because this assertion is meant to fail, this defer will be executing because the error was bubbled up at the exit of this block. Okay? And let's just see in action. Okay, so you see A is 1. Oh, sorry. A is 1 at in the first printf. Here A is 1, but then we have the third, its increment. So after this block, A is 2. And then this is a test assertion failing, saying, oh, look, I expected 0, but I found 2 because A is 2. And then we have the RDFR printing our nice phrase. No? So here we actually see test assertion failed, executing RDFR, because this RDFR was placed to be run whenever an error is bubbled up in this scope. Okay? RDFR is very useful, for example, for cleaning up memory that you have allocated in a function, that you want the function to survive. But if the function contains other piece of logic that may fail, you want to only clean up that memory if there is a problem after you have allocated it. So you can imagine, because manual memory management is a thing in Zig, you can imagine doing all sorts of allocations inside a block, and then having to either preserve those allocations outside the scope of the function, or having to clean them up if something went wrong in a later phase. And RDFR is meant exactly for that. Okay? Finally, for this, for the syntax number 1, we have dot file error. So here, what I'm doing, I'm declaring an error set, right? So as I said, any error is the global error set. When I create custom errors, in this case, I create a dot file error that I am defining myself. I declare it with a list of possible values for the error. And then using the double pipe here, I can merge it with another error set that comes, in this case, from the standard library fs file package. No? So open error is another set of errors that can happen when a file is trying to be opened. And in my function here, I have declared a function that wants to create a dot file. Let aside this comp time thing, we're going to discuss it in a bit. But the important thing is the return type here. So you can see I have said to the compiler that the return type is going to be either an error of type dot file error or nothing. So either a clean return or an error. And the compiler will actually enforce that the error that is returned is exactly inside this set, right? So, for example, if I want to create a dot file, but if the first character of the string that is passed as a name of the file is not a dot, I can return my custom type of error. So dot file error, invalid name. The name is invalid. When we are trying to create the file, we are not interested in the return file descriptor, so we discard its value. But if the file creation fails because, I don't know, inode are full, disk is full, memory failed to allocate, whatever, the try keyword will bubble up the error, and an error of type open error will be raised. So yeah, in this case, what I'm trying to do, basically, I'm just merging the directory that is passed as a second parameter with the operative system specific separator string and the name that is passed here. And if an error, and I want also to specify in the options that I want the file to be exclusive. So if the file already exists, please return an error. And this is a way of declaring anonymous types. So when you use the dot curly bracket, this is an anonymous type which type is inferred by the compiler at the moment of compilation. So in the test, given that we have now described this function, in the test, what I try to do to demonstrate how error handling does, I am assigning to the variable out the value of this function here that can fail, right? This is a function from the standard library from the FMT package, FMT namespace. It's printing doing allocation. In fact, it's called alloc print. you can see, because this function allocates memory, what we need to pass to the function is an allocator. So a piece of code that actually brings the memory from the operating system and from the hardware into our process heap. And this testing allocator is specifically helpful for tests because it will detect memory leaks and it will detect double freeze. It will detect problems with memory allocations at the end of the test. And this function is just taking the allocator. It could be any allocator. It could be page allocator on Linux. It could be a buffer, whatever. And it's taking the string and printing the string using the arguments that we pass. So in this case, when we pass 42, the meaning of life, it will allocate a string into the heap with 42 is the meaning of life, right? But if there is no memory, then this try will fail the test immediately because the try will bubble up there. And here, you can see where Zig really shines. So even memory allocation can fail. And, we could handle the error if we want. No? In this case, we are just saying if there is no memory, just fail the test. But we could be catching, we could be doing if. So we could be entering a whole new domain of possibilities of handling problems like this. At the end of the execution of the test, in the end of this scope, if this function managed to allocate memory, I have to free the memory that was returned to me by the allocator, right? Because in this case, allocprint is returning a slice of const weight, so a string basically, but this string lives in memory. And if I don't free that piece of memory, I have a memory leak basically. So yeah, basically if I remove this, if I remove this, the test fails with a memory leak. I can show that later. Let's go ahead. Here again, I try another assertion just to validate that my string is correct. And then I get into creating a dot file with a missing dot into the folder /temp. And then I can do the assertion that the error that I'm expecting is exactly the error that I had defined. This one will work because the file is valid and TMP does not have the same file. So at the end of the file, again, at the end of the test, I need to clean up the file because otherwise, since I have exclusive, it will fail the next test. And here we can see catch unreachable. You see? What I'm doing here is telling the compiler, when you go ahead at the end of the test and you want to delete this file, it shouldn't fail, right? We don't expect it to fail. But if it's failing, just give me a panic. Okay. Then we go ahead and try to create the same file, which will fail because this time we have the file already there. So we get this type of error, path already exists. And finally, we show the same syntax of switching into the error. So when we try, here we bubble up the error. Okay. We bubble up. Here we assign the error of create.file to duped. Because we don't have try here and this function can fail, this duped can either be the error type or the concrete type, but we know it's going to fail. So we are asserting that this is an error. And here instead, we are catching the error, putting it into E, and switching on its type. Well, not on its type, on its value, actually. I'm making confusion here. On its description, let's say. So either it is an invalid name, which is our custom error type, and then we perform a certain action, or we capture the error again and we print it for the user because we don't know what else to do. And same meaning here, but instead of using the catch E, I'm just using the if capture else error syntax. So these two blocks are equivalent in terms of functionality, but the syntax is a little different. So in this case,
sorry, but before you said is switching on the value, not the type. Is not but it's not a pattern matching on the type. So you have invalid the name and other type.
Error,
so it's not...
error is an enumerator, right? So it's not really a type, but it's its value. Yes, it is let's say descriptor. I don't know how to call it honestly in English, but it's that.
Okay.
So yeah, let's run this test and maybe see it in action. So this was the most complex one, I know. But yeah, okay. So you see, we end up in these two blocks, but everything else was passing. And in these two blocks, we have both methods both methods of catching the error and it returning the same error. Right? Let me show it again. Actually, okay. All right. Thread local. Very simple. When we declare a variable as thread local, in this case, I also used a arbitrary weight integer, so an unsigned integer of 6 bits. So this will fit a value that is up to 2 to the power of 6 minus 1. So I guess 63, I guess. Well, whatever. And in the thread local, I spawn two different threads. They all call into the same function that is accepting a value and then incrementing it by 1. And obviously, again, here, I am testing here, making the assertion. And because I know that this is going to work, we can put catch unreachable. Also because functions that are declared and to be executed in a thread, they cannot really return errors, right? They have to return void. Yeah, so this test will also pass because when the two threads complete, local head 1 in the thread test is not mutated. So the test, the thread of the test is still seeing the same value, right? Thread. There we go. And finally, packet struct. So my favorite here. We got guarantees from the runtime, for the compiler, that these two fields will be lined up exactly as they are declared in memory, right? Which means that this struct can be automatically converted from binary representation into the struct, right? Because every binary that fits this pattern of two 16-bit unsigned integers can be converted to coordinates. And in fact, what I'm doing right now here, down in the test, what I'm doing is, is exactly that. So I'm declaring the coordinates instance with the x-axis as 4 and y-axis as 2. Then I'm also declaring a value, random an array of 2 U16 with their binary representation. And then I can do this built-in function bitcast val. So the binary point representation of type coordinates, and you see I have to specify the type here because of bitcast. Bitcast is reading these two binary entries from the memory that is allocated for this array and is converting it to a coordinates type on the fly. And we can do that because this is a packed struct. So the ordering of the field is guaranteed. But I can also do the same from the memory of the type itself. So when I convert to bytes the memory representation of this variable, I can also bitcast that to another coordinates type, which obviously is going to be equal to the original coordinates. And that's exactly what we test in the assertions down here, right? We have the size of coordinates is exactly 4 bytes because these two unsigned integer fit into a U32. So the size is exactly 4 bytes. And point and pinpoint are exactly equal because the memory representation is exactly the same between this array and this coordinate struct. And also, point and pinpoint from memory are also equal because, again, when I'm converting to bytes, then reading the bytes and casting them to a type, of course, they just go back to the original struct. And you can imagine this is very helpful for making all sorts of optimizations into network protocols, into even payloads that you pass around and you want basically to get memory encoding for free. Pretty cool, huh? Right, so yeah, let's go ahead. Second feature that I really enjoy, and it's really what makes Zig different from the rest of the languages, it's comp time. So comp time is compilation time. And it's actually a keyword. We saw the keyword declared in one of the functions earlier. Comp time is a concept that's allowing us to run arbitrary code during the compilation time, during the compilation phase. We can do lots of things. Obviously, we cannot do a lot because we cannot have any side effects. We cannot make HTTP calls or other sys calls during the compilation phase. But what we can do is actually perform calculations or transform values directly during the compilation. Also dispatching types here and there if we want. No, I have an example in my OpenTelemetry SDK where I have counters, and the counters are assigned a type during compilation time. So when you declare a counter, you tell the compiler this counter can accept integer 64 or unsigned integer 16. So depending on that, you are going to shrink the memory usage because each of those counters are taking less space in memory because their bit representation is smaller. No? So this is very powerful. And what you do with comp time, if there is a problem in the logic that you're trying to execute, you return a compile error. And that is basically signaling that the compilation must fail because, again, comp time is run during literally the binary compilation. So with comp time, Andrew explains that he was not trying to do generics, but he first introduced comp time to originally replace macro expansions. And once he adopted comp time, then he discovered that basically generic types can be achieved with comp time, because what you do with a generic type is basically assigning it a strict type during the compilation phase. No, so you can see in the code here I put an observer function. This function is accepting a type of type t, and it's returning a type. Because type are expressions in Zig, you can accept as parameter and return as function, as argument returned to the function. And what this is doing, and you can see that in the code later, is effectively creating an observer generic type that is valorized or that is assigned the type t during the compilation phase. And that observer of t gets its own type of type observer t. You can also get pure generic functions, which accepts any type and then work on other arguments of the same type. You will notice if you read the Zig code that there is this idiom of declaring types, comp time types first. This is needed because you have to declare the type that you want to use in other arguments first. Otherwise, the compiler is not able to understand what these other arguments are assigned to. And a cool thing that you can do with comp time is not using the comp time keyword, but using the inline keyword. You can declare for loops and while loops with the inline keyword, and they will be unrolled and copied for each of the possible iterations at compilation time. So this is very helpful, for example, for achieving a form of polymorphism in tagged unions. So let's see some code again. I have a comp time file. You can find it in the repository as well. This is the basic functionality of comp time. You can see I'm declaring two constant variables, a and b, named 1 and 2. Then I also can specify that the constant c is of type comp time int. So I want this addition to happen at compilation time, right? So I want these two values then also to be known at compile time. They cannot be runtime known if I want to perform this. Okay? And what's happening in this test, because I'm also marking the try here with comp time, this test is never run. This test is only executing logic during its compilation, right? This is the beauty of comp time. everything that you see here in this test never touches anything after compilation. It's an op, right? All of the logic is performed during the build phase.
Well,
even the assertion.
Francesco, so during the compilation, it could be possible, for example, load data and create an executable with data, and then use the data during the runtime.
Load the data? What do you mean? You cannot read from disk.
Okay. Or from database or something like this.
No. I think functional people like to say you cannot have side effects in compilation, right? Because it's literally compiling. But you can do interesting things. For example, this type of assertion here. You can imagine testing other types of invariants about the data structure that you are getting. So imagine you are developing a library and you want, for example, the coordinates that we saw before, no? You want a specific piece of the library to only be called with positive coordinates, right? You can create comp time assertions like this one to ensure that users of your library are not putting negative numbers in there, even if the type is generic, right? And when you do that, you have a compilation error, which is not a bug in production. You have a compilation error and you are immediately told, look, this is happening here. So one technique that some companies are using that are adopting Zig is they will run debug builds with a lot of standard dot debug. Sorry, I'm messing up here. Standard dot debug dot assert calls, right? So the testing framework is useful, but this is the basic assertion thing that you can do. So standard dot debug assert, you should do like this. Right? So if you do this in a debug build, this is running in comp time. But if you also perform assertions at runtime in a debug build, that will panic, right? So a technique that some people is using is running canaries in debug build, in debug mode, with a lot of these assertions, because all of these assertions are no op in other release modes. For example, release fast and release small, if I'm not mistaken, right? Or even release small. I don't remember, but yeah, there are 4 build modes in Zig: debug, release safe, release small, and release fast, where you can imagine debug is like super safe, release fast is super unsafe. But if you can adopt this technique that you put assertions in your code either at comp time or at runtime, and then you run a small portion of your traffic in debug mode, and if you catch a panic, then you already know that you would have the same problem in production and you go fix it, right? So this is super powerful. But yeah, going again to comp time. Now, what happens if I run this test, right? Again, we said nothing is going to run actually, because this is only performing at comp time assert, right? Well, this is not good. Okay, so yeah, this is not even running. It's just compiling. Okay, I want to show here the generic type. You can see observer is a generic function that accepts a type and return a type. In here, you have this like anonymous struct that you return, but the compiler is going to map this struct with the type observer t. Okay, whenever you create one of these, for example here, and by the way, see how beautiful this is. You can declare tests even inside functions. Yeah, I just wanted to show this one here because it's super powerful. And by the way, this test observer, because it's named exactly like observer, will also end up in the documentation, just like what I was mentioning before. So what I'm doing here in the test, I'm creating an observer that is characterized with type U138. So 128-bit unsigned integer, and then the inner is set to 0. And then I call the update method calling the function counter increment. And then I, perform an assertion that the inner is being incremented to 1. So what I wanted to show here, this struct type obviously can have methods, and you can refer to them just like I did here by creating a mutable instance of the type, assigning it its values that are needed, and then calling into them. And the two functions here, pure generic function, as I showed before, I don't need to create a specific add 128 function for the type. I can just write one, and then I can, call it around when I populate it with, in this case, with counter increment. So that's the basic of generics in Zig. And finally, the inline loops. Also, this test is never running. It's just executing at compilation, right? Because we have a comp time variable named sum of type comp time int. We start with a 0 value, and then in an inline for loop, we go from 1 to 5, capturing the value of I and adding that to sum. But all of this is performed in the compilation time, such as that when I try to assert in the compilation time, the sum is exactly equal to 10. Okay? And again, I want to show that inline.
What happened if you, instead of using comp time at line 51?
Line what?
51. Instead of using comp time, you just execute the expectation.
I think it will not work, but let's give it a go. Sorry. No, it works. Yeah, it performs the assertion at runtime instead, because sum is already to 10 after the build. So when the test is compiled, the sum is already at 10. Yeah. So there is no reason not to work. But what I want to show, obviously, is that when you declare it with comp time, even the assertion. Oh my goodness. Time. Even the assertion is made at compile time.
Yeah. Got it.
Right. Let's go ahead. Last point that I want to bring that really makes Zig stand out, and it's going to be pretty fast. I don't have a lot of code to show here. The build, the Zig build file is entirely programmable in Zig. You can do all sorts of crazy things. You can actually go and fetch packages from the internet in this one. The build can be programmed to do all sorts of features. It can interoperate with C and C++. You can import .c, .h file. You can, compile C code for a specific target, compile BPF objects, and then embed them into your binary. It effectively replaces all the weird makefile, CMake, Bazel, Autotask, whatever you have in your project. And again, Zig fetch is as easy as running a command and you get immediately a dependency in your system. The way the build system works and makes things super efficient is by adopting a lot of caches. So every file is hashed and kept in a compilation intermediate representation state in a hidden folder in the project. I think it's called .zig-cache. And those are used to speed up compilation process a lot. Big projects still can take minutes to build, but normally in a matter of seconds you have projects built. Especially if you don't change much. If you don't change anything, it's instant. No, actually, I wanna do that here. I wanna show how it works. So, if I have this project here, and it's the same that we are looking in GitHub. So if I do Zig build the first time, I think it's not going to be super fast. Well, actually, 1 second. But if I do it the second time, it's just instant, right? So because I didn't change anything. And obviously, if I remove the .zig cache folder that I mentioned before, I now go back to building the project again, and it's probably going to take another 5 to 6 seconds, right? Okay. So yeah, you can literally do anything in the build system. Actually, let me show the build.zig file, which comes like this. When you do zig init in a project, it auto-generates for you the scaffolding. So you have this function build, which is called by zig build. And then you can, you can also add the return type as an error if you want. If you have to call fallible functions inside the build. And then you have, modifications to the build, targets. You can add static linking. You can define which files are going to be compiled as part of a library. You can define modules. You can define artifacts to be installed. You can define artifacts to be run, in fact. Right?
So they decided to use the language itself to
exactly. Yeah.
build system like Gradle with Groovy and
yeah. So super powerful build system. And again, I'm not a super expert of the build system. I've used it not as extensively as other parts of the language or the toolchain, but I can really see how it shines when I open other projects. So other projects have literally a build folder where they contain all their logic for the builds, and then they call into that by importing the build folder in build.zig, and they do all sorts of crazy stuff. Actually, I want to mention this link down here. Oh, apologies. This link down here is a GitHub organization where lots of projects are moved to the Zig build system, because remember, Zig can compile C code and C++ code. For example, let me open real quick one of this one. The repositories in here, you have SDL, which is a popular device library that was originally written in C. You have libgit, stockfish, the game engine, libuv, nuts C client, ffmpeg. All of these projects, if you open any of them, you don't have much other than build Zig. And what you are going to be able to do is just download the Zig version that is compatible with this repository, run the Zig build, and that's it. It will do everything automatically for you, right? So you can imagine how this mentality, these concepts can be used to improve in existing code bases that are in C, even Sigo, if you like. You can compile Sigo with ZigCC. So yeah, maintain it with Zig, folks. Finally, I want to mention some challenges when you are going to adopt Zig for the first time. I already mentioned manual memory management. That's the biggest hassle, especially for me, because I came from Java and Go, which are garbage collected. So entering the mindset of understanding the object's lifetime and assigning the ownership, that was not easy at first, but you can get used to it. You can practice, and it gets a lot of value in the end to be able to do this type of programming. The debugging tooling right now, it's a bit immature. You don't have the same experience that we have with IDEs like IntelliJ or even VS Code. Of course, there is possibility to debug code with LLDB. There is a new tool that was presented in one of the Zig shows last month. It's called Microscope. Very good, but still a bit in its infancy. I don't want to say immature, but it's very young. So debugging is not as easy as it should be, but it will get better. There isn't a string abstraction. You only have slices or arrays of bytes, which I mentioned before. There are no interfaces, as in the OOP meaning. So you don't have an interface keyword where you can attach and define methods, and you can implement those. There are some alternatives, the tagged unions. So if you create a tagged union and then you create a method in it with an inline switch, you can sort of achieve compile time polymorphism, but also runtime. there is a field parent pointer, which is a built-in that I have used, and it's it's not super easy to understand at first, but basically it allows a function with some metaprogramming to access the parent structure that is passed of a pointer that is passed into an argument of a function. So that's a way of connecting two different implementations. And finally, if you really want dynamic dispatch, you can roll your own vtable, just like other languages do for you. You create the definition of the interface and then the vtable and the methods that are going to fulfill, and then you can subscribe them into the vtable at runtime. Understanding the type coercion is not so easy at first, again, because when you don't specify the type, the inference, so the rules that the compiler applies, especially to arrays and slices, are not easy to grasp, let's say, immediately, but you can get used to it. Just know that these challenges are here. You shouldn't let yourself be, scared by them, because I guarantee you, in the end, they will make you a better programmer. Understanding how really these type of things work internally, it helped me a lot, honestly, in also working more effectively with other languages. So yeah, I'm really thankful that I started up this Zig journey. Why Zig is so relevant today? Here is where really I want to emphasize how exposing ourselves to the understanding of a lower level of the stack helps us make better decisions when we write software for our users, right? We mentioned earlier that we don't write software just for the sake of it, right? So what we want to do is understanding the behavior of our software internally and understanding how it interacts with the rest of the ecosystem that is around the software. So, CPU, memory, network, right? We have to expose ourselves to how certain concepts that are complex in nature are handled internally. Because if we don't, and we don't pursue this understanding, then our lack of understanding results in software that does not deliver all possible features that it should handle, right? Fortunately, it is not as easy as it sounds to get to this, because there is no dedicated training, or it is not most companies' jobs to train people on how systems work at low level, or at lower level at least, right? You can see that with LLMs. Everybody's just teaching LLMs how to build code, but they are not explaining how LLMs are actually giving you the code that you see. And this can create disconnect between the people that are supposed to understand what they are putting in production and the people that are actually putting the code in production, right? And it's not good. Finally, the rise of cloud computing and infrastructure as a service in the last 10 years also was not super helpful, because again, more abstraction, more disconnect between what happens really in the machine versus what is provided to you by the cloud provider. This is not necessarily bad, but what I'm saying is that sometimes you don't need those abstractions, right? Sometimes you don't need to just package a container and put it in the cloud and let Google run it for you, because you really want to take care and understand what that container is doing internally, right? Linux is 35 years old this year, guys, and there's a ton of knowledge in there. So there are problems, hard problems that are solved in the Linux kernel, just like nothing, nowhere else. So state-of-art technology is in the Linux kernel, which is written in C. There is some part of Rust right now, of course, and understanding that, nobody can fit the Linux kernel in their head entirely, no? So why do we want to throw away that knowledge? No, we don't. We want to reuse that. We want to be able to cooperate with that, interoperate with that knowledge that is buried in there by reusing the same data structures, no? And Zig, we can do that with Zig. If we import the headers file from the kernel, we can build a BPF code that uses the same data structures, the same definitions in the header files. It's actually pretty powerful with Zig as a concept. The proliferation of frameworks is something that we know. There is a JavaScript framework to make a+1 or to increment an integer. So with this proliferation of frameworks, sometimes people in companies, that especially junior developers, are taught to work with the framework. So they are taught how the framework works, not how it delivers its functionalities. And this is a bit of a risk if you think about it, because then what happens when that framework changes or is not delivering a feature that the engineer needs? No, so if it's not understanding what the framework does internally and it's just relying on the framework, you are limited. You are scoped to what the framework gives you. But also, again, understanding why and how things are done certain ways is not a job for everybody. No, sometimes you don't have time or resources to do it. And finally, for Zig specifically, there is a tendency right now to have very vertical products. So there is database that only stores vector embeddings, for example, right now. So there are some use cases where performance, where security, where logic needs to be handled with care, that are just perfect for Zig because all of the features that we saw, so comp time, the build system, and debuggability and understanding and expressiveness of the code, they allow really to focus on one thing and one thing only and do it very well and solve a problem for everybody and build on top of that in the future. So that's why Zig is relevant. But also because, sometimes we are given too much. Sometimes we are offered too much technology. What we have on the left here is Bob Knödel. He's one of the most prominent Flat Earthers, Flat Earth movement content creators. And in 2020, 2021, the Flat Earth YouTube channel presented a video where they bought a gyroscope, a laser gyroscope, which is a very sophisticated instrument. It basically detects drift in the speed of light across atoms, if I'm not mistaken. So it's a $20,000 instrument that is used in spacecrafts, and they bought it, or they were gifted it, to prove that the Earth is not rotating, so the Earth is flat. On the right here instead, there is Eratosthenes of Siena, which in 2050 BC measured the circumference of the Earth with a stick, using the shadow that was casted by the stick on the Earth, and knowing that the shadow was not present in Alexandria. So he measured the difference between the shadows and derived the angle and the arc of or the length of the arc of the Earth between Siena and Alexandria, and from that, with some trigonometry, he calculated the circumference of the Earth with an error of 2%. So what I want to say with this analogy, sometimes technology is not needed. You don't need a super advanced technology or super powerful instruments if your basic assumptions are wrong. Sometimes what you really need is going back to the basics, understand the problem in its root, and figure out the simplest and cleanest, most possible dumb solution to get to a conclusion. Well, I wouldn't say dumb, but I would say simplest, and it's you can do that. So take this analogy with you and apply it to your software, and see if you can deliver the same software with less, instead of trying to add more onto it just because you would like to try something new. Sometimes what you want to do is just go to the bare bone of what you need and build on top of it piece by piece. That's the philosophy I think Zig really makes shine if you are trying to build software in this way. I want to leave some references to the products that are in production using Zig today. So Tiger Beetle is a financial database, time series database, transactional database for finance transactions. ZML is an inference machine learning stack. ZAND is also a framework for building machine learning on microcontrollers. BAN is the JavaScript runtime. I guess some of you is using it. BAN is written in Zig. Ghosty, the terminal that you've seen here, is entirely written in Zig from scratch by Misha Hashimoto, the co-founder of HashiCorp. Zine is a static size generator made by Loris Crow. MicroZig is a framework for embedded controllers to use small hardware boards. And River is the default window manager in Arch Linux, is also written in Zig. Now, there are much more products. I think these are the biggest one right now. And they've been using Zig for years right now. And they are all saying well about it. So I hope your next project can also be including some Zig in it. And with that, I thank you all for looking into the stream and joining the stream and being with me and with us. You can find me on my website, on GitHub, LinkedIn, and X. I, again, want to share the link with you of this repository so you can go home, or like you are already home. You can take the code, run the Zig test, just like we did in the presentation, and find out by yourselves, by tinkering with the code, the beautiful things of Zig. And thanks a lot again for being with us. And now we go into some Q&A.
Yeah, we have a couple of questions, Francesco. One is related to
should
the
I
code
stop,
that you showed before.
Wait, before the question, should I stop sharing, or are we going to show the code again? Let me know.
Maybe you have, for this question, you have to show the code.
Okay.
So let me show you the question. So how does it know that there is a plus operation on T? I think the last code that you... Okay.
Sorry, I don't... Okay, here. Okay.
So...
does it... I guess we are talking about this?
Yes, I think the stuff
Here?
related to the add. Yes, Angelo said, how does it know that there is a plus operation on T?
Because the type is known at compile time. So if this would be a thing that is not summable, it would be a compile error.
Okay. Wait a bit if Angelo wants to reply.
By the way, I should mention, because of Zig search in simplicity, there is no operator overloading. So this plus is always a plus. And it tries to perform the sum operation on all possible types that support it. Okay.
For example, if you use toString,
to array, I don't think you can do that, because array concatenation is double plus. So probably if you use two slices of, actually slices are not compile time known, so they must be coerced to arrays. Right? So they are a constant array with a fixed length. It's not a slice, because slice has the backing array and a pointer to the backing array, but it can be resized at runtime.
Okay. Angela said, okay, so we can go to the next question. So Mario said, let me show you. If we see the C competitors, we have Rust that move away the manual memory allocation from the user in favor of borrow checker. No, you know the borrow checker in Zig instead allows manual memory management. No, so again, Mario said, do you believe Zig decided that to favor simplicity? Any additional thoughts?
I honestly don't know why this decision was made. I can suppose the borrow checker lifetime RAII model doesn't really fly for what Zig tries to do, because Zig tries to be explicit. Zig tries to be expressive. Okay, so whatever you don't see, for example, the drop call at the end of a block in Rust, that's hidden behavior. So my assumption, but we should speak to Andrew Kelly about that if you want. You can ask him in the next conference if you like. Is that because of this philosophy, this milestone that he wanted to not have hidden behavior, the same logic of applying allocations and deallocations without them being seen or exposed to the users made the principle fall. So he decided, let's keep it this way, which makes perfect sense in my opinion. I hope this addresses your question, Mario.
I give you 1 minute. I think yes, because it doesn't reply. Anyway, so I think that there are no other questions. So I don't know, Marco, if you have some super last question to Francesco.
No question for me. And I want to say thank you to Francesco. And
sorry, I was logging because Angelo said the creator of Zig is a strong believer of St. Thomas. So
maybe it is.
Anyway, yes. So thank you, Francesco, for this talk. So
thank you so much, Giovanni, Marco, Mario, everybody in the Meetup organization for having me. It was incredibly helpful for me to show Zig to you. I hope that everybody of the watchers are happy about this presentation. Otherwise, leave me a feedback using my social connections, and please give Zig a try. And yeah, if you are not happy with that, just reach back to me and I will make you a coffee.
Yeah, I think from this evening we will try the Zig Zen, above all the Zig Zen command.
Thanks again.
Okay. Thank you.
Thank you all. Bye.
Bye-bye.